Thank you. So I'm Ajitesh Srivastava. I'm a research assistant professor in the Electrical and Computer Engineering department. And I'll talk about informing public health with epidemiology, humans, and AI collaborations. And we'll talk about this in two parts. The first part is how humans and AI can potentially collaborate for forecasting. So first, I would like to mention how research translates to policy and situational awareness in the field of infectious disease forecasting at the public health level. So it's never that a single model or a single team drives these decisions or drives this information. The way it's been done even before COVID-19, since I believe 2012 or so, is you have multiple forecasting teams. Each of them independently produce forecasts. And then there will be an ensemble team. Sometimes this ensemble team is the CDC itself. Or sometimes there's another team that works with the CDC to prepare these ensembles. And this is the ensemble is what goes on the CDC webpage for situational awareness. So how do they build these ensembles? Well, they're simply just mean or median. So basically, each of you give me your forecast. I'll take the mean and I'll consider that to be the true forecast, right? And sometimes you try to come up with a linear combination of all the forecasts, but this median forecast has been the most consistently correct or accurate forecast, better than any other individual forecast. So it performs well, but there's scope for improvement. So particularly, there are certain times during the epidemic when we know that these ensembles or even the individual models don't work that well. Which is around changing trends. So for example, if there's a surge about to happen, or we're increasing and then a peak happens. But these are important points, right? These are the things that you want to know about. So why don't we use more sophisticated machine learning algorithm, right, in the age of AI? What's stopping us? Well, the two inconsistencies here. First, there's behavioral inconsistency. So models change over time. So, I may have a model submitting to the ensemble, and then next week I think, well, maybe I should tune this parameter and then resubmit, right? So every week I'm submitting something different. There's no consistency. Whatever pattern you may learn from the past, like we do in machine learning, won't apply, it won't generalize. So there's that issue. Then there's the participation consistency, right? So, I'm submitting this week, maybe next week I'm on vacation or funding runs out and I'm no longer in this project. So in a given week, you have 10 teams submitting. The next week, you suddenly have 5 and then 15, right? So you don't have consistency in participation. And if you're trying to build machine learning algorithms treating each of these forecasts as features, you want the same set of features every time. So what do? Well, the state of the art is still looking at the median. And we know that the median has different performances across different phases of the epidemic. And then second known result we have is that aggregate shape of submitted forecasts, this is from our prior work itself, that if you just look at the shape instead of the numbers, if you look at the shape, they're pretty good at predicting the right shape. It's just we're bad at predicting the right numbers. Okay, so how can we combine these two ideas? So here's the approach we have, where we look at the model forecasts of individual teams, we extract the shapes out of those, and then we use that as extra feature into the median ensemble. So then that is passed through this quantile random forest. The random forest looks at, well, if this were the shape and these are the forecast, how should I modify these forecasts to be better consistent with the ground truth? So that is our approach. And what is the shape? How do we extract these? We have derived some mathematics behind this, and this can be discussed more offline. What we see particularly is, there's a long tail there, and most of the times it's hard to see which model, which ensemble performs better. But this is basically errors. Weighted interval score, it's a way of measuring errors in probabilistic forecasts. Particularly, there are these peak times, which is, let's say, January 2022. This is the Omicron time of COVID-19. A lot of these ensembles will have these high peaks in error, and what we see is our approach produces much lower error around that time. So now I'd like to move on to how epidemiology and AI can collaborate. And I would talk about this in the context of this problem of variant emergence. Um, so we know a new variant appears due to mutations. A variant of COVID-19, influenza, all viruses mutate, right? Um, and then the variant spreads due to human interactions. The first problem, I believe, is very hard to predict how mutation will happen. It's some randomness there. But how it spreads, well, someone has to be infected, then travel somewhere, and then infect others. So there's some human travel pattern there that could be leveraged, right? So I believe this is easier to predict. Also, as William Shakespeare has said, what happens in the UK does not stay in the UK. And you can see this on different COVID-19 variants. If you see here, the purple line, for example, is the alpha variant. That appeared in the UK, and after a few weeks, it appears in Sweden. And then there's the Delta variant, the red line appears in the UK, and after a few weeks appears in Sweden, right? So there is some pattern there. There's some sort of delay. And then you'll see not all variants appear in both countries at the same level. Some variants, hit, let's say, the orange line hits about 30, 40%, but in UK, just not even 20%, right? So based on that, we propose two problems. Like, given the prevalence of a variant in different regions, A1, A2, or different countries, we want to predict if the variant will ever reach a certain proportion in this given country, right? And then the second problem is delay prediction. Given the prevalence of a variant in different regions, predict when the variant will reach a certain proportion in this region, right? The first problem we found is easier to solve. Second one is slightly harder to solve, and we'll focus more on the second one now. So the general contributions we have is we derive, perhaps for the first time, the dynamics for the delay detection between two regions. So purely, not from machine learning point of view, purely from just mathematics, just looking at the dynamics. But then what we do is we look at this mathematics that we have derived, and we just pick some important features that we think would be helpful for a machine learning model, right? So we believe that the dynamic model will not be perfect because it's done under some assumptions, but then the machine learning algorithm helps us to maybe see how the assumptions are being violated, right? So we do all these derivations, and one thing scientists are very good at is looking at a plot and drawing a straight line. Right, and that gives you a hypothesis like, yeah, maybe something like that should be an equation. And then under certain assumptions, you can derive that equation. So that's what we did. And we'll skip the math. But then there are certain things we see here. There's a term SI that seems to appear in these equations. And then there's this Rij, which is like the prevalence ratio of two variants. And this gives us a straight line. So it looks, it makes the patterns easier to digest. Straight lines are good for machine learning also. So we use these in our graph neural network. So graph is constructed by travel patterns, and the features, we just show these extra features which we derive from the math. And just doing so, what we see is that the dynamics-based model, which is purely based on math, has very good median error, but very bad mean error. But our machine learning model, which combines lessons learned from the mathematics, has good median error as well as good mean error. And I'll stop there. Thank you.